Hi, I'm Leo. Today I want to explain the vibe coding journey of building a PCI subsystem over network. This project is part of my Human in the Loop series, where I use AI to develop true no-man's land projects, problems that require deep Linux domain knowledge and do not come with an existing playbook. So this is really a double experiment. It is a test of AI's ability to work in deep kernel space engineering, and also a test of the human-AI co-working model. AI for speed and implementation, human for architecture, judgment, and first principles control. In these two slides, I will show the core idea. First, how Linux actually models PCIe internally, and then how that understanding leads to a virtual host bridge design for PCIe over TCP. Let me start with the key idea behind this picture. When most people think about PCIe in Linux, they imagine the kernel directly touching physical hardware everywhere. But that is not really how Linux sees the system. Inside Linux, most of what we work with are software abstractions. Bus objects, device objects, driver objects, mapped resources, and kernel-managed state. In this diagram, the dashed box at the top is user space, and below that is the kernel's software world. That is the first important point. Linux does not operate on the raw PCIe fabric directly. It operates on a software model of PCI. The PCI subsystem, the driver core, the device model, and the memory abstractions are all software structures that let the kernel understand and manage the system. Now, from the CPU and kernel point of view, memory and PCIe are handled in a very similar programming style. They both appear in a unified address space, and Linux can access both with reads and writes. So at a very high level, RAM and PCIe MMIO look similar. But the behavior behind them is completely different. RAM is passive. We read it, we write it, and from software's point of view it behaves like sequential storage. But PCIe is not passive memory. Behind a PCIe address there may be an active device with its own logic, internal state machines, queues, engines, or even very powerful compute units like a GPU. So when software writes to PCIe, it is often not just storing data. It may actually be sending a command to a live hardware system that keeps working after the write completes. That is why Linux introduces more structure for PCI devices. First, PCI configuration space is accessed through PC_ops. That is how Linux enumerates devices and reads or writes PCI configuration registers. Then bars are mapped into kernel virtual space through PC_imap or irmap, and once that mapping exists, the driver uses MMIO operations like RETL and RITL to communicate with device registers. For complex devices, a register write often acts as a doorbell. Software prepares buffers or descriptors, rings the doorbell, and the device starts processing asynchronously in hardware. Later, when it finishes or needs service, it signals back through an interrupt. So the real hardware boundary is actually very narrow. It is mainly PCI config accesses through PC_ops, bar-based MMIO accesses after bar mapping, doorbell writes that trigger device work, and interrupt delivery back into the kernel. In a full implementation, DMA is also part of that boundary, but for this slide I want to focus on the control path. And once you see that, the PCIe over TCP idea becomes much clearer. To implement PCI over TCP, I do not need to rewrite the Linux PCI software model. I keep Linux's local view intact. The PCI bus, the PCI device abstraction, the driver model, and the driver logic all stay where they are. What I need to do is transport the hardware-facing messages across the network. So PCI config transactions from PC_ops are forwarded to the remote target. Bars can still be represented locally, but the actual MMIO reads and writes on those mapped regions are sent over TCP to the remote side. Doorbell writes are forwarded so the remote device can start its work. And interrupt events generated remotely must be sent back into the local kernel so Linux still feels like the device is attached locally. So the big message of this slide is this. PCIe over TCP works because Linux is already built around software abstractions. We do not need to re-implement all of PCI inside Linux. We only need to intercept the narrow set of places where Linux actually touches hardware, and remap those interactions across the network. Now to build PCIe over TCP, I introduce a virtual host bridge. And I say virtual not simply because it is software. At this level, Linux already treats most of PCI as software objects. I call it virtual because this bridge is not backed by a local physical root complex. Instead, it acts as a local PCI root for hardware that is actually remote. This is the key design move. Above the bridge, Linux still sees a normal PCI hierarchy. The kernel core stays the same, the PCI subsystem stays the same, and the driver still thinks it is talking to a local PCI device. So I do not rewrite Linux PCI. I only intercept the hardware-facing operations. PCI config accesses through PC_ops are forwarded to the remote target. Bar MMIO accesses, after PCI_AMAP, are redirected over TCP. Doorbell writes are sent remotely to trigger device work. And interrupts generated by the remote device are delivered back into the local kernel. On the target side, VFIO provides controlled access to the real PCIe devices. So the target machine owns the physical hardware, while the local machine owns the PCI software model. That is the whole idea of this slide. Local above, remote below. The virtual host bridge is the illusion boundary that keeps Linux unchanged while moving the real hardware boundary across the network. Before I let AI go deep into the PCIeoverNetwork implementation, I first built a controlled testbed. This part is very important because for a project like this, the hardest challenge is often not just writing code. It is harness engineering, building an environment that AI can repeatedly observe, modify, reset, and test. Without that, AI will drift. With that, AI can iterate much faster. So to make the coding process easier and more reliable, I set up a virtual system with two machines, a host and a target. The target machine owns the real PCIe hardware. In this setup, I attached two NVMe drives and one real GPU, an NVIDIA GeForce RTX 4060 to the target. So the target is where the physical PCIe devices live. The host machine is where I build and test the PCI over TCP logic. This is the side that will eventually create the virtual PCI view and try to make those remote devices appear local. So the split is very clear. The target owns the physical devices, and the host builds the software illusion. But the testbed alone is not enough. To really make AI coding productive, I also need a repeatable test workflow. That is why I built a test workflow with Make automation. Using Make, I can reset the environment, bring up the host and target, attach devices, run the connection steps, execute test cases, and collect logs in a consistent way. This matters a lot, because it turns a fragile manual kernel experiment into a reproducible engineering loop. From the AI point of view, that is critical. AI is much more effective when the test path is structured. Instead of guessing what to do next, it can follow a clear workflow. Start the testbed, enable the target devices, connect from the host, run the tests, check the outputs, and then debug or refine the code based on the results. So this slide really shows two layers of harness engineering. The first layer is the system harness. A host machine, a target machine, and real PCIe devices attached to the target. The second layer is the workflow harness. A make-based automation path that lets me repeatedly drive the whole experiment from setup to validation. Together, these two layers make the project much more AI-friendly. They give AI a stable environment, a repeatable test loop, and a much smaller search space. And for a no-man's land systems project like PCIe over TCP, that kind of harness is often what makes the difference between random experimentation and real progress. Now let me show a real demo of how this works with an NVMe drive. At this point, the goal is no longer just architecture. The goal is to prove that the whole PCI over TCP path actually works end-to-end in a repeatable way. For this demo, I use the Make automation workflow to drive the full process. First, I reset the environment so both sides start from a clean state. Then I sync the latest code, compile it, enable the devices on the target, and connect the host to the remote target. In other words, the whole bring-up path is wrapped into an automated test flow instead of being driven manually step by step. That matters a lot because a systems demo like this is only meaningful if it is reproducible. I do not want a one-time manual success. I want a workflow that can be run again and again, both by me and by AI during iteration. To validate the NVMe path, I also add a file integrity test. The idea is simple. Once the remote NVMe drive is exposed through the PCI over TCP path and becomes usable on the host side, I copy files into the file system, copy them back out, and then verify the MD5 checksum. This gives me an end-to-end correctness check, not just that the device enumerates, but that real storage I/O works correctly through the full stack. So this demo is showing more than just discovery. It is showing reset, code deployment, build, device enablement, remote connection, block device usage, file system access, and data integrity verification, all inside one automated workflow. And that is the point of this slide. The project is not only an architectural idea. It is backed by a reproducible test loop and a working NVMe demo that checks both functionality and correctness. This is not the end. With AI coding, every solution is just the start of the next loop. The project continues and so does the human-in-the-loop journey.